Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to do a live stream. Actually, right now we're going to do a live stream. So this is pretty exciting. Okay, the way we've done this before is that I've taken 3 comments that people have posted on StatQuest videos or on the community page, and I'm going to go through those comments, and then at the end, I'm going to take comments from the chat. So we'll take some live comments and questions, and we'll just see how it goes. All right. I'm just really excited. Thank you for being here for my second live stream ever. I think the plan is to do it twice a month, at least for now. Uh, Once in the evening my time and once in the morning my time. I think that kind of covers the whole world. We get Asia, we get Europe, we get North America. Um, so just tune in for the time that works best for you. All right, let's talk about our first comment. Okay, um, I'm terrible with people's names, so I'm not even going to try to read this one, but you see it on the screen. This is a great question, and the question is, what is your favorite machine learning algorithm? Now, um, obviously that's a tricky question. But what I want to say is my personal use of machine learning is different from a lot of other people's use of machine learning. Um, Most people, when they use machine learning, what they really want is they just want to get the right answer all the time. And that sounds reasonable, right? However, I'd like to do research. And when I do research, what I want to do is I want to understand sort of underlying mechanisms and underlying structure in my data. And I'm actually willing to sacrifice a little bit of the accuracy in order to get more insight into my data. And so, one of my all time favorite machine learning algorithms is actually called random forests. And I know these are simple, and I know they're basic, and I know they're not the best, but they give me insight into the underlying variables. They're very easy to interpret as to what they're doing and why they're doing it. I like that. I love the fact that I can take any type of data. I can take continuous data. I can take discrete data. I can take categorical data. I can throw it at random forests, and random forests will give me clustering of it. I can get a visualization as to how things are related, um, and how the samples are related. Um, I love that. Um, what else does random forest do? Gives me insight into the data, allows me to graph, and oh, the last thing that I love about it is it gives me an estimate on how much confidence I should have in the prediction. Now, a lot of the methods will do that. Well, they'll give you some confidence. However, the random forest one is so easy and so simple and easy to calculate that I just kind of love it. For example, say like I get I've got my random forest, it's all trained, it's ready to go. I give it some new data and I want to make a prediction with it. Well, imagine I had 100 trees, just for this example. Imagine if all 100 trees came up with the same answer. And if that was the case, I'd have a lot of confidence in that random forest kind of like was very confident about how it made its decision. Uh, in contrast, imagine only 51% of the trees came to the same conclusion. Well, in that case, I would have a little less confidence in the output from it. And I just love how simple it is. I can just easily see how many trees were involved in making a decision or a classification, and I can let that be a guide as to confidence in the output. So, for those reasons, random forests are my favorite. Don't get me wrong, though, I love a lot of machine learning algorithms. I mean, I wouldn't be making videos about them if I didn't think they were all kind of interesting and cool. But I'm just saying, personally, for the kind of work that I do, I'm a big fan of random forests. All right, so that gets a bam. Bam! All right, ready for comment number 2. So, another name I'm not going to try to pronounce live. I know it's embarrassing. I think maybe one day we'll just have a contest of names that I just can't pronounce. Um, and it'll, we'll all laugh and it'll be a good time. But I think this is a great question. The question is, what is data leakage in machine learning? So let's talk about what data leakage is. Okay, so we start with a data set. That's sort of what all machine learnings do. We start with data set. Now, this is going to be an example of data leakage in machine learning. We use that data for training, and then we use that same data for testing. Using the same data for training and testing is an example of data leakage. It's a crazy, over-the-top, totally obvious example of data leakage. It will cause us to overestimate how well our model will perform with real data because we've trained and tested with the exact same data set. So that's a big no-no, and we all know that. Obviously we didn't learn a lot from that example, but now we at least have a sense of what data leakage is. Data leakage is when our training data set is not independent of our testing data set. Okay, so here's an example of what we should be doing. We should make a training data as a subset of the original data set, and testing data should be a subset of the original data, and they should be completely independent of each other. Now we train the model with the training data, and we test the model with the testing data. When we train and test using separate data sets that are independent of each other, we avoid leakage. Okay, that's all obvious. No big deal. Okay? However, leakage can be sneaky. Okay, here's an example of super sneaky data leakage. We start with the original data set. And in this original data set, we've got some missing data. Do not impute the values first and then split the data into training and testing data sets. Don't do this. This is because when we use all of the data to impute values, then that means the testing data was involved in filling in this value, and the training data was involved in filling in this data. So these two data sets are not independent of each other. And as a result, once we do our machine, we train and we test, we're going to be overly optimistic about how well this method is going to perform. So this is a kind of a tricky thing. Instead, what we should do is we should leave the data that's missing, we just leave it, and then split the data into training and testing data sets. And now we impute the missing data in the training data set just using the training data set data. And we can impute the missing data in the testing data set just using the testing data set data. Now the training and testing data sets are independent of each other, so we can avoid data leakage. All right, so that gets a double bam. Double bam. Super exciting. Okay, so we're making great progress. We're moving along pretty fast, which is good. And now that means we're ready for comment number 3. Give me just a second. Let me get this ready. Okay. So this is a question of just my process of how I do my work. The question is, where do you learn these nitty-gritty details from? And the answer is the internet, Google. What I do is I find... So what I'm showing you right now is an example of a web page that I found that described XGBoost. And what I do is I Google and I read everything, every single thing. And oftentimes when I'm reading something, I don't understand it. It's very complicated. It's mathematical. It's got this weird notation. It's complicated. Words I've never seen before. And I'll read it and I'll go, okay, that didn't make any sense to me. So then I'll move on to the next thing and I'll read that, and maybe that makes sense to me, maybe it doesn't. If it doesn't, I just keep going. And sooner or later, I'll Google the words I don't understand. I'll Google the terms I don't understand. Sooner or later, I'll start getting a picture in my head. And once I start understanding little pieces, I'll go back to where I started and I'll reread everything. And the stuff that didn't make any sense before will make a little bit of sense the second time. It'll usually, it brings on new questions. It makes me, um, maybe I understood one thing, but now I don't understand another thing. So I got to keep reading. I've got to keep Googling. I got to keep looking for new sources of information. And then I just go back and I go back and I go back until everything makes sense. Okay. So I do tons and tons of reading. And that's the first phase. And that can take, to be honest, that can take anywhere from a day to a month to a year. Believe it or not, my PCA video, I spent about 2 years on that video alone. It's not like all I did for 2 years is work on that video, but I was constantly reading and constantly getting more background information, just a little bit every day until I finally said, okay, I got it. I figured it out. I know how we can visualize it. I know how we can tell this story in a way that no one's ever done it before. Um, because I've done all this research. Once I've done the research and I understand what I'm doing, I go through all of the materials and I annotate it and I do the math and I redo the math myself and make sure it makes sense. Um, I'll just keep trying to figure out, make sure everything works the way I was expecting it to. And I'll just derive everything. And so what I'm showing you right now are notes from how I prepared for the XG Boost uh, StatQuest that I've been working on. We have at least 2 more coming out in the next couple of weeks. I'm really excited about. We got the nitty gritty math details coming out, and then we've got a video on optimizations. Um, so, anyways, that's how I do what I do. Oh, one last thing before we move on. If it's possible, I will run a basic data set through the algorithm and make sure it does everything I'm expecting it to do. And I do it one step at a time, and I make sure I can do everything on paper as well as, and it matches exactly what I'm getting with the computer program or the machine learning algorithm. Triple bam. All right. So now we've come to the part of the live stream where I get to take questions from you. And I'm super excited about this. This is one of the more fun parts of it. So let's get down to it. I'm just gonna start. I'm gonna put up this screen, and this lets me go over to the chat room and see if we got any good questions over here. Let's see. Wow, we've got a lot of good chat going on. A lot of hellos. Um, what do we got? Uh, I see someone wants to see power regression step by step. That's a StatQuest. That's not really a good question to answer on the air. Someone else wants more sessions on RNA-seq, DNA-seq, and next generation uh, sequencing. Oh, interesting. So, Uma Shankar Shreddy, I think I pronounced that name right. She's asking about R squared and why we can't trust it, and why sometimes we come across a model yielding an R squared that's greater than 1. Um, and also to talk about the adjusted R squared. Okay, interesting question. Um, I'll be honest. Um, I've never actually seen an R squared greater than 1. I've seen R squareds less than 1. That's when your default model is just the worst. It's worse than um, the most simple model. And it can happen every now and then. A lot of people have pointed that out to me. Um, but I will talk about adjusted R squared. So here's the deal with R squared or any correlation metric. Say like we're doing a linear model. For example, say like I'm modeling height using a person's weight and using their age and maybe some other variables. Okay, so I'm just trying to predict someone's height. And R squared will tell us roughly how strong the relationship is between the variables I'm using to make the prediction, weight and age, and what the other variables are. Uh, so R squared tells us the relationship between those and the thing that we're actually predicting, which is height. Um, Now, here's the thing about this type of model. If I added a bunch of random noise to that, say like I added someone's astrological sign, I added the name of their pet dog, I added, um, I don't know, what time of year it is, um, uh, stuff like just kind of random stuff that should have nothing to do with height. Well, so when we do linear regression or something like that, if the variable is really bad and doesn't help at all, the parameter in front of it will be zero and that variable will just go away. It'll effectively not exist. But if just by random chance that variable helps even a little bit, and it's completely unrelated. It should be uncorrelated, but just because of the way random noise sometimes work, it helps a little bit. Well, then it'll remain in our linear regression model, and as a result, our R squared will increase. And that's no good because we don't want the R squared to increase. And that's what adjusted R squared tries to compensate for. So the more variables we add to our model will never get worse because if the variable's really bad, the parameter will be zero and it'll be as if we never added it. However, the model can get better for all the wrong reasons because we've added some sort of random noise that just happens to help out. And so because the variable tends to fit the data better, even with random variables, the adjusted R squared compensates for that by penalizing for the number of variables we use to predict something. So our adjusted R squared can be super useful. Okay, so that's what we're going to talk about for R squared. We're going to move along and see what else we got. Uh, oh, actually, and here's a question, not necessarily a technical question, but Yan Hao Chen asked for me to classify my videos into different levels of difficulties, if that's possible. And if you've ever gone to my website, statquest.org, I have a video index. And generally speaking, that index is within each category is ordered from simple to complicated. So at the very top, I've got a section called the basics and statistical basics. And at the very top, it's got the most basic concepts for statistics, and they just get more complicated as you go down that list. Um, um, if you go into the machine learning app part of the page, it starts simple and it works its way down to more complicated. So it's already pretty ordered. Oh, here's an interesting question. Skylar Dimsworth asked, is it important to learn all of the formulas and equations even though we already have advanced statistical software to help us do the work? And the answer to that is it depends. It depends on what you want to do. Um, do you just want to use these algorithms and be a user, or do you want to be sort of an in between, sort of semi power user, someone who knows all the ins and outs, or do you want to be that kind of person who's deriving the next generation machine learning algorithms? Uh, Obviously, if you want to be deriving the next generation, understanding all the formulas is super helpful. Um, in between, it's maybe not super important to memorize all of them. It's good to go through them and to get a sense of. Oftentimes, when you go through the math, you can kind of see where the strengths and weaknesses are. Um, However, personally, I think as long as you understand the main ideas, you're good to go as a practitioner. It's sort of like the executive summary. That's the most important thing, are the main ideas. And that's typically the way I structure my videos, where I'll have like a main, like for XGBoost, I've got some main ideas videos. And the longer we last, the more nitty gritty the details are that we cover. Largely because I think the main ideas are the most important, and the implementation details or the actual mathematics are kind of sort of important, but not as much important, at least from my perspective. Unless, like I said, you want to be that person making the next generation machine learning algorithm, yeah, you better dive into that math and learn it well. All right, let's see what else we got. Oh, this is a funny one. Shravan Kumar says, "Can you build a model to pronounce all names from different parts of the world?" That would be great. I love that one. Um, I wish I could. I'm going to spend more time working on StatQuest videos. Maybe someone could come up with a way to help me with this. If so, post it in a comment. That would be awesome. Um, um, ah, uh, Phil Thompson just put a comment. He said, "I purchased an introduction to statistical learning, but didn't know that I needed to know calculus in order to truly understand the book." Um, yes, you need to understand calculus. However, if you have an opportunity, I don't know if I should be saying this on air. Return the book. You can download it for free. You don't actually have to buy it. Um, the calculus is in there, right? There's a lot of calculus in the Introduction to Statistical Learning. You can skip it. Um, Read the introductions to each section. You don't have to get into the nitty gritty details. A lot of the examples and the introductory material doesn't have calculus. And if you understand that, you understand 90% of what you need to know. So that's my recommendation. So even if you can't return the book, it's still a great book to have, and it's good to support the authors that wrote the book. Um, I mean, that's in a great book, and I love it. So yeah, if you can support them, that's great. But don't freak out if you can't do all the math. You don't have to do all the math. Just read the introduction to each subject, read about the examples that they use, and you can still learn a ton. It's a good book. All right. Uh, ah, a lot of people are asking for time series, and the answer to that is um, yes. We're going to do time series possibly over the summer. Uh, hopefully in the summer. So here's what the deal is. We've got XG Boost for the next month or so. I've got a couple of like odds and ends housekeeping videos that I just kind of want to put out. I've wanted to update my p-value video in for years, and I finally have it as a two-part what is the p-value, what is a p-value, and how do you interpret it, and then a second video on how to calculate. They're both super short, but I want to put those out. Um, just because I really need to update my p-value video. And then after we've done those sort of odds and end videos, we're going to do neural networks. And after neural networks, we're going to do time series. And so I think that'll be in the summer. It could be early fall. I'm looking forward to it. There's a lot to learn, and it's a pretty exciting field. uh, some people have been asking about Bayes, naive Bayes. That may be one of those odds and ends videos that comes out in a month or so. Um, we just have to see kind of how the scheduling goes. I am going to have to research neural networks for a while, so there may be a little bit of a downtime where like I said, I'm just reading every single thing I can think of as the topic, and I'm trying to come up with a new way, a way that nobody else has done before, a new way to talk about neural networks. Because if I just repeat what everybody else says, well, you might as well just go to everybody else. So I'm going to try to come up with a StatQuest way to talk about neural networks. Um, what else we got? Yeah, I'm gonna take one more question. Let's see what we got. Ah, can I talk about Pearson versus Spearman correlation? And the answer is yes. Uh, if that's an odds and ends video, uh, um, that comes out in a month or so, that would be great. Otherwise, it'll come out maybe in between neural networks and time series. That's just something I've wanted to cover for a long time. It's been on the to-do list for years. Different correlation metrics. It's important to know all of them, or at least have a familiarity with them. So that's the plan. So for all these questions, we have a bonus BAM. So thank you very much for your questions. I love it. Um, and thank you very much for joining my live stream. It's a real treat to have everyone here and get all the support from everybody. So until next time, the end.